You ever look at a really tall, skinny structure and just feel a little uneasy? Well, you're not wrong to. There's a hidden danger lurking in these designs, a kind of failure that is so sudden, so dramatic, that for the longest time it was a total mystery to engineers. So let's dive in and crack the code on this hidden failure.
Okay, take a look at this water tower. We've all seen them, right? But have you ever really stopped to think, why all the extra metal? All those crisscrossing beams and supports? It kind of looks like overkill. But trust me, every single one of those pieces is there to fight off a very specific and very scary kind of collapse. And it's called
buckling. And here's the thing. It's not about the material shattering or breaking apart like you might think. Nope. It's something much stranger, and in a lot of ways, way more dangerous.
Look at this. You have a perfectly straight, stable column. You put it under just the right amount of pressure from the top, and it doesn't just get a little shorter. Wham! It suddenly bows out to the side and completely gives way. That is buckling. It's not a failure of strength, it's a failure of stability.
So, how does this sudden snap actually happen? Well, it all boils down to a single, crucial number.
Engineers have a name for it, the critical load. The easiest way to think about it is it's the absolute limit. It's the maximum possible weight a column can hold up while staying perfectly straight. It's balanced on a knife's edge, right at the tipping point of going from stable to not.
And that's the really terrifying part. If you go over that critical load, even by a teeny tiny amount, the column doesn't just sag a little bit, it can trigger a total catastrophic collapse. Instantly, with no warning. So what in the world determines that critical load? To get that, we need to look at a much simpler model. All right, to really wrap our heads around this, let's zoom in. Forget the giant column for a second. We can actually understand this whole thing with a simple model that shows you exactly what forces are at play. So picture this. You've got two stiff bars, connected in the middle with a hinge, and there's a spring trying to keep them standing up straight, and all the while a load is pushing down from the top. This super simple little contraption, well, it holds the entire secret of buckling.
It's basically a tug of war. The spring is providing what we call a restoring force. It wants to pull everything back to the center and keep it all nice and stable. But at the same time, that downward load is creating a disturbing force. It's trying to push that middle hinge sideways and make the whole thing just fold in on itself.
And here you can see what happens when that disturbing force gets to be too much for the spring. It just gets overwhelmed, loses the tug of war, and the whole system buckles. It completely loses its stability and collapses.
So this whole battle leads to one of three outcomes. If the spring is stronger, the system is in what we call stable equilibrium. You can nudge it, but it'll always pop back to the center. If the load is way too strong, it's unstable. The slightest disturbance and it collapses. But right at that perfect tipping point where the two forces are perfectly balanced, that's neutral equilibrium. And that exact point of balance is the critical load. Now, for centuries, engineers knew this happened, but they couldn't predict when. It was this terrifying wild card in construction. And then one guy came along and found the beautiful, elegant math hidden inside all the chaos.
And that guy was the brilliant mathematician Leonhard Euler. Back in 1757, he developed a formula that could precisely calculate the critical load for any given column. I mean, this was a massive breakthrough. It literally changed engineering forever.
And this is it, Euler's buckling formula. Now I know, it might look a little intense, but the story it tells is incredibly powerful. And once we break it down, it's actually surprisingly simple. So it really just comes down to three key things. First, E. That's the material's stiffness, how much it resists being bent. Then there's I, which is all about the column's shape. Think about how an I-beam is way harder to bend than a solid rod with the same amount of steel. And finally, L, the unsupported length. Now look closely. The length is squared on the bottom of the fraction. That is a huge deal. It means as a column gets longer, its resistance to buckling just plummets.
And what's really amazing is that Euler's work doesn't just tell us when something will buckle. It can predict the exact shape it's going to make when it fails, whether it'll be one big simple curve or a more complex S shape. It is an unbelievably powerful tool.
Okay, that's the theory. So what does this all mean for building things in the real world? How do we actually use this to design things that don't suddenly snap? Well, the formula gives us a truly profound insight.
And here it is. This is probably the single most important and honestly the most surprising takeaway from all this. To stop buckling, how stiff your material is matters way more than how strong it is.
which is totally backwards from how most of us think, right? We think stronger is always better. But in this case, nope.
The source material we're looking at puts it perfectly. Most steels, whether they're high strength or not, have basically the same stiffness. So using a more expensive, stronger steel gives you absolutely zero advantage against buckling. It's the stiffness that does all the work.
And that brings us right back to our water tower. Now you can see exactly what all that bracing is for. It's not really adding strength. What it's actually doing is chopping up those long legs into smaller, shorter sections. It's reducing the unsupported length, the L in Euler's formula. And since that L is squared, making it just a little shorter makes the whole structure dramatically, unbelievably more resistant to buckling.
Once you get this principle of buckling, you start to see the world in a whole new way. You start to notice all these elegant and sometimes totally invisible solutions that are all around us.
Seriously, think about it. The legs on a simple chair, the frame of your bike, even a drinking straw you try to push down on the table, they are all designed around this one hidden force. So now that you're in on the secret, what are you going to look at tomorrow and never, ever see the same way again?